Hi and welcome back to my channel, or welcome to my channel if you are a new viewer. Can you work out the value of x in this problem you can see on the screen? Now we have got a line B to D, which is a diameter of the circle, and then we've got a chord A to C, which has lengths from A to E of 4, E to F of 2, and F to C of 3. And we have another line segment from B to F, which meets the chord A to C at a right angle. Can you work out the length of B to F? If you want to solve this problem yourself, pause the video now. Otherwise, I'm going to go through my solution in 3, 2, 1. Okay, so the first thing that I wanted to do with this problem is to take the line B to F and extend it, as you can see. And that makes the point G on the circumference of the circle. I then introduced a new chord, D to G. Okay, now from there, I know the angle in a semicircle is 90 degrees, and it doesn't matter where that angle is in the semicircle, as long as one of the sides of the triangle is the diameter of the circle, then the angle opposite will be 90 degrees. So I know angle BGD, as identified on my diagram now, is a right angle, is 90 degrees. Okay, now the next thing that I wanted to do is label F to G Y, and you'll see why in a little bit, but I'm going to label that for the moment because that will be useful. I want to try and work that length out, F to G, because then I know a method which we will get to later on, which will help me to work out X. Now I'm going to introduce a radius here, and I'm going to introduce this radius, well, slightly shorter radius, but a line that would be the radius if I extended it, that joins up with the chord DG and meets it at 90 degrees. Now, the reason I want to make that line meet the chord at 90 degrees is because I know, and if that's 90 degrees at H, DHI, then I must also have 90 degrees at EIO, EIO, because we have got corresponding angles, and the lines O to H and B to G must be parallel lines because they are meeting that chord D to G at the same angle, okay, at 90 degrees. Right, now that brings me on to this bit. A radius, we haven't quite extended it to be a radius, but we could theoretically. A radius bisects a chord at 90 degrees. So if O to H was extended, was a radius, would bisect or would meet the chord at 90 degrees, that means therefore that it would bisect it, and that means cut it in half. So I've labelled it here X and X. Okay, that just signifies that they have to be the same number, they have to be equal. Now, that brings me on to the fact that we've got AC is equal to 9. So looking at this chord AC is equal to 9. I'm going to half that because my O to H line would bisect it because it meets the chord A to C at 90 degrees. So A to I must be 4.5. That means E to I is 0.5 and I to F is 1.5. Now, I know that IFGH will have right angles in all four corners, so therefore it's going to be a rectangle, and therefore I to F must be the same as H to G, and so we get that also being 1.5. Now, we know, as I've used several times already, or spoken about several times, that a radius bisects a chord at 90 degrees. Because O to H meets the chord D to G at 90 degrees, that would bisect it, meaning therefore that H to G, 1.5, is the same as D to H, which is also 1.5. Okay, now we're getting somewhere because what we're finding here is that we've got a few similar triangles because they've got the same angles in them, obviously, but they've got different lengths. So the next thing is to consider two of those triangles, EIO and DHO. Now the lengths for EIO or E to I is 0.5, D to H is 1.5. I don't have a length for I to O, and I don't have a length for H to O at the minute, but what I can do is I can label I to O Z, and that would make H to O, well, H to I, because we've got that rectangle there, like I said earlier, I to F, G to H is a rectangle. I to H is the same as F to G, which is Y, and then we add on the I to O, which is Z, and we get Y plus Z. Now the scale factor there is timesing by 3. So Z times by 3 gives me Y plus Z. So that gives me that 3Z is equal to Y plus Z, which if I rearrange it, gives me that 2Z is equal to Y. I'm then going to put that onto my diagram. So I've replaced the Y with 2Z. Okay, now the next thing I want to do is consider still this EIO triangle, but also DGB. Okay, this larger triangle. Now, the base of that is going to have a length of 3, and B to G is going to have a length of X plus 2Z. Now, my scale factor here is timesing by 6. 0.5 times 6 is 3. So Z times 6 is X plus 2Z. Again, we'll put that as an equation. So 6Z is equal to X plus 2Z. Take away the 2Z from both sides. We get 4Z is equal to X. Divide both sides by 2. So I can get 2Z. So 2Z is equal to X over 2. I can replace the 2Z now on my diagram with X over 2. Now, we've pretty much done it. We just need one other thing, and this was the method that I was alluding to earlier, which is why I wanted to work out that length Y, or what was originally Y and then was 2Z. So we are going to use intersecting chord theorem. Now, intersecting chord theorem states that if you've got a length A and a length B and C and D identified in this diagram, so circumference to the intersection point times by the other end of the line on the circumference to the intersection point equals circumference to intersection point times circumference to intersection point. AB is equal to CD. Now, for our problem, we want to work out X, obviously, and we can use A to F times by F to C is equal to B to F times by F to G. Okay, now if we substitute in for what those lengths are, A to F is 4 add 2, which is 6, times 3, and B to F is X times by F to G, which is X over 2. Simplifying that, we get 18 is equal to X squared over 2, because X you would times by the numerator of your fraction, so X times X is X squared over 2. Times both sides here by 2, and we get 36 is equal to X squared. And then square root, and we get an answer of 6. Obviously can't be negative 6 because it's a length, so it has to be positive. Pretty neat answer, but at least in the way I solved it, quite a complicated solution. That does use, well, 2 circle theorems from your national GCSE, at least here in England, but 3 circle theorems from the IGCSE, the international GCSE, with that intersecting chord theorem. Okay, so yeah, pretty neat solution. If you got it, let me know down in the comments below. But before I finish, I want to say thank you so much to all of the people that have subscribed and have helped this channel get to 1,000 subscribers. I really appreciate all of your support, and yeah, I want to make sure that you know that if you watch the video this far. So thank you so much for helping the channel and for helping me and supporting me on YouTube doing these videos. Okay, now if you like this video, as always, please remember to drop a like on it. It helps me. And if you want to, check out one of the other videos over here somewhere. There'll be another video over here. Have a great week, everybody. And I'll see you next week, 5 PM, Monday, for another problem-solving video. Until then, bye-bye.